Welcome to discussion 22. In today's discussion, we'll focus on section 4.3 on the shape of a graph. And in this video, we'll do a practice problem finding local extreme points and inflection points of the function f of x equals the cube root of x. All right, so I want to first give you 8 minutes to try this problem. So 4, 3, 2, 1, pause it and try just part A for 8 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 8 minutes. Let's talk about it together now. So let's begin by rewriting this function as x to the 1/3 so we can take the derivative. And let's first find the critical numbers and local extrema. So critical numbers and local extreme points. Alright, so we will need to take the derivative. Okay, so this is just power rule. The 1/3 comes down, and I'll get 1/3 x to the negative 2/3. And then we can rewrite this and bring that x to the negative 2/3 to the denominator to get 1 over 3 times x to the 2/3. And now I want to know when this equals 0 and when it's undefined. So my derivative would be equal to 0. This fraction would be equal to 0 if the numerator equals 0. But that's not going to happen because the numerator is just 1. So my derivative never equals 0. So then when is this undefined? So our derivative is undefined when the denominator is 0, and that happens when x is 0. All right, so next we go to a number line. So we take all these points that made the derivative either equal 0 or that made the derivative undefined and plot them on a number line. Even if these numbers are not in the domain of the original function, we would still put them on the number line. In this case, though, 0 is in the domain of the original function, but regardless, even if it wasn't, if it's something that made the derivative 0 or undefined, it would go on this number line. Okay, so now, I think with this function, we could probably just handle it all together. 1 over 3 x to the 2/3. So, okay, so we'll have that. So this is our derivative. This is our f prime of x. And then based off of that, we'll write down what's happening with f of x, the original function. Okay, so with this x to the 2/3, I want to notice that this means we are going to cube root the x and then raise that to the second power. So when we have this even power, this 2, the even power, because of that, so our output can't be negative. Because even if the cube root of x ends up being a negative number, when we square that, it'll be positive. So this will be positive on both sides. And if my derivative is positive, the original function is increasing. It is going to be rising. Here as well, it is going to be increasing. It'll be rising. All right, so we are now ready to state our critical numbers and classify them. So for our critical numbers, so our critical number is x equals 0. Remember, critical numbers are things that make the derivative equal 0 or be undefined. The one thing that we have to check is our critical number needs to be in the domain of the original function. If it's not a critical number. And if I plug 0 into this original function, there's no issue with that. I can do the cube root of 0. So this is in the domain of f. Okay. And because my function doesn't change what it's doing, it's just increasing on both sides of it, x equals 0 is not going to be a local max or a local min. I'm going to say it's neither a local max nor a local min. Okay, so we found our critical number and we've classified it. All right, we are ready for inflection points. Okay, the next part of the question said to find inflection points. To find the inflection points. Notice the question didn't say to write down the intervals where it was increasing and where it was decreasing. That's why I didn't do that. It just said find critical numbers and determine which are local maxes and mins. So that's nice. It saves me a little bit of writing there. But if we needed to say where it's increasing or decreasing, we could use our number line to do that. Okay, inflection points. We need the second derivative now. Okay, so if we take the second derivative, let's write this in thinner pen. So let's do second derivative. That will end up being, if we take the derivative of this, our first derivative, the negative 2/3 will come down. I'll get a negative 2/9. And we'll get x to the negative 5/3. And I could rewrite this as negative and then 2 over 9 times x to the 5/3. And now I need to say, when is this second derivative 0 and when is it undefined? So our second derivative never equals 0. Because for a fraction like this to be equal to 0, the numerator has to be 0, but that can't happen because the numerator is just 2. Okay, then I write down where's the second derivative undefined. And it is going to be undefined when the bottom is 0, and that happens when x is 0. Okay, so now we take these, we put these on a number line, and we're going to make a sign chart of the second derivative. Okay, so the only point that I got where the second derivative either equals 0 or it's undefined is x equals 0. So I put a tick mark there. Okay, and for this function, I am going to just put the factors because I see a negative number and I don't want to get that mixed up. So I'll put the negative 2 over 9 altogether. And the other factor is x to the 5/3. But if you wanted to handle it all together, I think that would be okay for this function. Okay, and now I'll keep track of my second derivative and what that tells me about the original function. All right, so let's separate these into rows. Let's separate out some rows, and then I'll separate out columns. So negative 2 over 9, that is just negative. That's going to be negative everywhere. And then x to the 5/3, now I don't have something like an even power. I have an odd power, this 5. So this is going to be positive when x is bigger than 0. But if x is less than 0, it's going to be negative. Right, because this is cube root of x, and then being raised to the 5th power. And if x is less than 0, the cube root of x is going to be negative, and a negative number to the 5th power. That's still going to be negative. Okay, so if we put these together, a positive times a negative will give me a negative, and then a negative times a negative will give me a positive. When the second derivative is positive, f is concave up. And when the second derivative is negative, f is concave down. All right, so we're ready for our inflection points. So inflection points. Okay, in this case, we'll just have one. It occurs when x equals 0, since the concavity switches. That's one thing that I need for something to be an inflection point. Concavity has to switch or change, and it changed from concave up to concave down. And the other thing that we need for something to be an inflection point is that f, our original function, needs to be continuous at that number, at x equals 0. And if we go back and look at our original function, see, our original function was all the way up here. 0 is in the domain of this function, so this function is going to be continuous at 0. It's one of our known functions, so these are continuous at every value in their domain. Alrighty, so I'm going to underline this. So this question, I think, didn't just say find the x value of the inflection point. I think it said to find the inflection point. So that means to get the x and the y. Okay, so let's do that next. Let's go to the top of this side of the page, and let's write down the whole point. Okay, so the x coordinate is 0, and if I were to plug that into my function, the cube root of x function, the y coordinate would be 0. So that is my inflection point. All right, just for practice, let's use this information now to graph this function. Okay, so we talked about how to do this in lecture. What we need to do is combine the sign charts of the derivative and the second derivative. So combine those sign charts. So we're going to combine our number line. And we put a tick mark at any point that we put a tick mark at on either of those two sign charts. So for the f prime sign chart, we put a tick mark at 0. And for the f double prime sign chart, we also put a tick mark at 0. But we already have one there, so I don't need to put another one. Okay, and then I'll keep track of my derivative and my second derivative sign, and keep track of what does that tell me about the shape of f. Okay, so if we go back to our sign chart for our derivative, let's see, this was positive on both sides. Okay, so this is also going to be positive on both sides of 0. And then our second derivative sign chart, let's see, that was positive to the left and negative to the right of 0. So let's indicate that. This was positive to the left of 0 and negative to the right of 0. Okay, so for the shape, when our derivative is positive, our function is increasing. When the second derivative is positive, our function is concave up. So I need increasing concave up, that has this shape. For the next column, derivative is positive, so it's increasing. Second derivative is negative, so it's concave down. That means it's going to have this shape. All right, let's put this together and draw a rough sketch of the graph. So y equals cube root of x. So I'm going to draw some axes. Okay, so to the left of 0, it's going to have this shape. It's going to have this shape. And to the right of 0, it's going to have this shape. So something like this. That's the graph of cube root of x. And I took this for granted a little bit, but I know that it goes through the point 0, 0, because we found that that was a point on the graph. This 0, 0, this was the inflection point. And I can see that in the graph. Our graph seems to change concavity there, from concave up to concave down.